Welcome to the Future of Power podcast, where we explore how fault-managed power is revolutionizing energy distribution and driving a smarter, safer, and more sustainable future. As the inventors of fault-managed power, Vault Server is at the forefront of this transformation. With FMP now part of the National Electric Code, this breakthrough technology is entering the mainstream, unlocking new possibilities in power delivery. In this podcast, we bring together industry experts, innovators, and thought leaders to discuss the challenges, opportunities, and game-changing potential of FMP. Join us as we have meaningful conversations, share insights, and explore what's next in the future of power.
Okay, welcome back everyone to the Future of Power podcast. I'm James Eves, Director of Building Electrification at Volt Server, and I'm joined again by Steve Eves, our founder and CEO and the inventor of fault managed power. How you doing, Steve?
Great. Thanks for hosting, James.
You're welcome. I wasn't supposed to, but I'm happy because I like doing this. How's the weather in East Greenwich?
Crappy. I feel like a wet cat in a freezer. Yeah, it's like 40 degrees out. May in New England.
That's terrible. It's a little warm here. It's just like a little bit too warm. But, it's okay because there's a pool and I'm going to barbecue tonight. But, it could be 2 degrees lower and that would be perfect.
Yeah, I know how you like to torture us when you're in California.
Yeah. All right, let's get going. I like I said, I wasn't supposed to do this. Rona, I don't know if you know Mike, but Rona is our chief revenue officer, and she's sort of the expert in data centers. So I had to do a little prep, a little research to kind of catch up on this topic. But I found it really interesting. And I was thinking about a half an hour before we started, like why is it so stimulating to learn about like power distribution in data centers? And so I'm just curious, it's a little test. I want to see if either of you, and Mike, I'm going to introduce you in a second. I'm holding the punch. But I'm just curious about what, if you guys are find this a particularly interesting use case for power distribution and why, what's interesting about it to you?
Well, as a business, we chase watts of power. So from the business side, I just love chasing things that need a lot of power because that's what we sell. But from a technology side, a data center is a really complicated facility. It involves power distribution, but also a lot of redundancy, resiliency, right? Control and monitoring. So it's a really nice business for fault managed power because fault managed power is a combination of power delivery and data. It's a great fit for us.
How about you, Mike?
So I think it's, early on when we were talking about applications, for fault managed power, I was thinking, boy, it'd be great if we can somehow adapt this to data centers, because with all the load is within the servers, right? As at least the critical load. So, and what do UPSs do? They convert AC to DC, then back to AC, and then transmit AC, and then eventually what do the servers want? DC. It's yeah, let's just keep it at DC as much as we can. And not only that, but also the safety. There's a lot of safety. You're dealing with a lot of power, a lot of safety concerns you're always dealing with as far as arc flash and keeping your fault currents low and whatnot. So the safety of fault managed power is very appealing for data centers. So I was thinking, this is a great application. So, Steve and I have talked about it a lot. In fact, we set up, dedicated meetings just to pour through on how we do it. And then that evolved, as we'll get into, that evolved into the study we did last year. And now we're turning the page on that. No pun intended. Well, sort of, but we're turning the page on that because of the changes in the industry.
Yeah. It's similar to me. I came from an academic background as a researcher. And what I realized, and this is funny because this is how me and Mike met. I was just telling Mike before we started the show that, I was thinking about the first time we met, it was because of this. I was having this sense, this level of interest that I don't know how to explain it, but this feeling I had when I was learning about it that reminded me of the time when we were, about 5 years ago when we were investigating power distribution in CEA, like in greenhouses and indoor farms. And what I really liked about that was like the interaction between plant science and electrical engineering. Like you're kind of designing, optimizing around both those systems. Um, but with data centers, it's like the computer science is like driving this so hard, like this design so hard, and that everyone like it's everyone, all the professions have to kind of coordinate really tightly because everyone's kind of getting pushed their limit. Like you have to, like the HVAC engineers, electrical engineers, architectural engineers, everyone's being challenged because everything's like this constraint. Every aspect of the design is so constrained, and it's just like so you have to learn at least a little bit about all those different disciplines to kind of have a holistic understanding of what's going on, with the power distribution. And I'm not saying I don't claim to have a deep understanding of all those areas, but you learn a little bit about each, and it's really exciting. Um, which is a good segue to introducing Mike because I think Mike is an expert in this industry, right? So Mike Sorego is a principal engineer at Southland Industries, and for those of you who don't know Southland, Southland's one of the largest and most respected MEPs in America, and they do a ton of data center design and optimization. A year ago today, Mike and Steve published this paper called "A Comparison of Fault Managed Power and Traditional AC Distribution in High Performance Data Centers." And today I want to use that article, kind of go back to that article and use it as a roadmap for this discussion. And but the first thing I want to do is just sort of like level set. And something we talked about, in the prep call was that one of the challenges with designing these data centers is it's kind of a moving target, right? The technology is moving so quickly that the underlying technology is moving so quickly, it makes it challenging to design systems to like deliver power to these servers. I wonder if am I saying that correctly, and can you expand on it a bit?
Yeah, sure. And I wanted to bounce off your point with the CEA, which is Controlled Environment Agriculture, for those who don't know the acronym. And that did get the juices flowing and the wheels turning in regards to, the application of this for data centers, because the application in CEA is the lighting, which is a large amount of load in a small amount of space. And what do drivers want? DC, ultimately, right? Because the drivers are converting AC to DC. So that tunes you into, that server application on how to do so. But some of those solutions are similar, like say a year or several years ago, the solutions may be similar because of the densities, but getting right into the meat of it, James, with the densities we're talking about, we did the study last year. We were saying, well, we were modeling around, 25 kW rack and whatnot. And at the time that was very reasonable, but now, those densities are, with AI are getting higher and higher. So there's a lot of challenges there using the traditional methods that we do data centers. Now, those methods have evolved, but they've over time as those rack densities increased. But the technology that was being traditionally used for these data center rows of racks was keeping up because we were just we're still living within their means, if you will. Like the busway we were using above the racks was, at one time maybe 200, then it evolved to 400. Now we're looking at multiple runs of 1200 potentially to reach these densities, which becomes more and more cumbersome. Now, and Southland being primarily we're design build, so we're primarily a constructor. We're on the engineering side. We're deep within the constructability of these data centers, rather than just putting lines on paper. What's in the back of our minds are how is we actually going to construct that, and that's where we offer a better perspective on the solutions, because the physical fit and the safety of the installation, the safety of the use for that matter, is paramount for us.
Okay, so for someone who hasn't built one of these data centers, Can you just kind of help like us visualize like the key components of delivering power like inside the data hall to these server racks?
Sure. Yeah. So a lot of data centers, to your point, they're large. They have lots of power, as everybody knows. So it uses a scheme called block redundant distribution. And what does that mean? Well, when you're buying and designing or and installing electrical equipment, you want to stay within the means that the manufacturers can develop them quickly. So you want to live within their rules as far as sizes. Like, just to give you an example, you want to live in the switchgear size of maybe 3,000 to 4,000 amps because it's something they're used to producing. They have all their UL listings for. So you want to stay within those units. Obviously, you need much more of that. So how do you develop a large facility using those sizes? Well, you put together blocks. You call them power blocks. So you utilize those, and then you use them to create redundancy. So you can use it in two major fashions: either distributed redundancy or isolated redundancy. In distributed redundancy, I'll use the example of saying, well, one data hall will use 5 blocks of power, so 5 sets of usually what that means is transformers, generators, and switchgear, and that's your power block. And then you'll have a large UPS in there to pick up your critical load. So you'll balance the load equally across 5 power blocks, but the capacity of the data hall can be handled by 4. So if you lose any piece or one whole data block or one whole power block, then the rest of them just pick up the load just fine, right? So, and that's called distributed redundant. Now, in isolated redundant, you have an additional power block where you have your normal power blocks handle your load, but you have one that sits idle until you have a failure of a component or an entire power block, and then that is the reserve block or the catcher block, as it's sometimes called, and that picks up that load that has failed, and then what the equipment you need in that case for the critical load anyway is what's called static transfer switches, which transfer that load to that power block, that reserve power block, in an instant, in a fraction of a cycle, which is very fast, and it does not perceive it as an outage at all. Like, the servers do not perceive that as an outage at all because it happens so quickly. Now, that's a very expensive and technical piece of equipment, obviously, so that plays into the whole complexity argument. But that's a basic rundown. We could talk about many details about that. So I hope that suffices as a good description of how you distribute power in an AC data hall.
It does, but makes me want to ask which one's better, or is there one like how do you decide which of those two designs you use?
Well, the distributed redundant distribution system is typically a more economical way to go because those static switches are expensive, and because you have that reserve block, which is considered the extra block. Now, you may say, well, so does the distributed redundant, but you don't have those static transfer switches in there, and that means you don't have also those extra feeders. Distributed redundant, you're utilizing everything that you're providing. Maybe in the case I proposed, it was 4/5 of a capacity. So that lessens the cost, but it also makes the math tricky. Meaning you have to distribute your load in multiples of the blocks, and it makes the math a little bit tricky, so you don't have overloads. So using an isolated redundant takes the burden off that math, if you will, in your distribution, so that you have a little more flexibility in how you lay out your data hall, as opposed to handcuffing it to multiples of 4 or 5. Does that make sense, James?
Yeah. Distributed redundant is, in terms of, it's a higher capital utilization, right? It's using less equipment. But isolated redundant, you're paying for basically flexibility. You're adding more equipment to have increased flexibility.
Yeah, you could put it there. And there's some finer points to it, but I mean that's the gist of some major advantages.
Oh, okay. All right, last question about that. I don't want to get too far down if I find this really interesting. So if I'm a data center, like an operator, I want to build in optionality, because I think, it's hard for me to predict what my customers are going to ask me to install. Say I'm a colo, and in 3 years from now, I'm worried about, right now we're designed for 20 kilowatt racks, and I'm worried that 3 years from now there'll be 50 kilowatt racks. Would that impact which one of those designs? Would the isolated redundant system give me more flexibility in order to be able to adapt more quickly or easily to like unexpected changes in the market like that? Is that the type of flexibility it provides?
I think so. For in the colo market where there's uncertainty about your layouts and who you're serving, I think the isolated redundant lends itself better because it gives you that flexibility. If you know who your client is going to occupy those halls and you have a good sense of their system architecture, like how many racks and at what capacity and how many rows they have, then you can say, well, we could do this distributed redundant. But keep in mind, though, because of the math involved with the distributed redundant, once you get above like 5 blocks, you tend to sway towards the isolated redundant, just because it starts getting way too complex. The more blocks you have, like if you want your data hall to be, 8, 9, 10 megawatts, then you're looking at isolated redundant, because it just becomes too tricky to do the distributed redundant method.
I get it. Okay, so my next question is, the challenge is, right? We're talking about a challenge of putting this equipment in. It's expensive, right? I get it. Right now, what's driving the market is increases in peak densities, right, for these server racks. Power peak densities, peak power densities, excuse me. And so I get this feeling as I'm learning about this market that's a big problem. It's a big design challenge. But you just described a bunch of components to me. And so my first instinct is like, well, they're making a lot of money from these GPUs, right? What's the big deal of just, running new busway, installing new PDUs? Like, why not just add more equipment and you're done with it?
Well, the challenge is the increase in density of the racks, because yes, you're adding more stuff, but you're trying to get to a finer point, if you will, physically. So when we did our study, we did 25 kW per rack, and that was at the time we began the study, that was the going rate. But now we have clients asking for planning for 200 kW per rack. It's an immense difference because when I mentioned the busway before, you can get a plug-in busway is a very common AC method for distributing above racks, and oftentimes you'll have two. In fact, can't think of a time where we didn't have two, because you want that redundancy. So above every row, you have two of these things. Well, once you get a row of say 10 racks at 200 kW, you're way beyond what feeding one of those with a single busway, because you just run out of amps, you run out of power. So you have to use multiple runs of that busway. Now there's a way you can do it from both ends, say run two lengths from both ends. But if you say, I want 200 kW and 10 racks in a row, you can't do that anymore, because you're beyond even that 1200 amp limitation for plug-in busway, or where you can plug in outlets and drop cords and whatnot to it. Or module, those tap boxes that have the, either drop cords or outlets. That's, what you'd ideally use. So then you need a solution for those ancillary racks, or maybe a couple racks on the end that you need to either provide a short run of busway, or maybe even dedicated outlets. It makes it inconsistent, right? So you can't really apply those traditional methods at those densities anymore. And then, if you use multiple, you can only serve from two ends. So if you need more than two, then you have to have some that are higher, overlapping, zigzagging, all that stuff. And they all need clearances. All those boxes need clearances to be able to twist them in, to utilize them in the future, to plug in your outlets. Not to mention, the NEC clearances. You need to access them in case you have to go disconnect one in an emergency. So there's a lot to it. Once you start getting at that, packing that much power in a tight space, things start running over each other, and you can't buy code, and you can't buy any reasonable safety.
But can't you just it's a customer asking you for this 200 kW racks today, right? So can't you just design around that in anticipation, like just build a bigger building with more power distribution inside it?
Right. You can put more power distribution around it, but you still got to get to that point where you got to distribute within that rack, that row that they're used to.
Oh, I get it.
So you have, and you're going to have some level of containment. So you have a row across from it too, so that you can run your AC. Now, a lot are liquid cooled, but there's still some air cooled components that aren't liquid cooled. So if you use liquid cooled chips, you still have the rest of the server that still requires air cooling. So you're still using that traditional containment, the hot aisle, cold aisle air distribution. Even if you have doors, you need room for that kind of airflow, even though you're cooling the chips with direct liquid. So you still have that traditional physical architecture of the rack. So you're still, even though you could have all the land in the world around to put your gens and your transformer and stuff, you still got to converge on that traditional rack pod, if you will. Does that make sense?
Maybe. I'm not the data center expert, so you're gonna have to talk dumb to me or talk to me like I'm dumb. Like for instance, why can't I just spread everything out more? Do you know what I mean? Like it seems like what you're describing is a density problem. Like these buildings, like I start running out of space. Like either in the vertical spaces above the racks or on the floor or really close to the racks themselves, right? Is that what you're describing? Like I'm having space constraints.
Now, yeah, in regards to the IT infrastructure and why this stuff is close together, I'll tell you what, I'll let Steve answer that because he had some really good insight. He knows a bit more about that than me as far as the IT infrastructure and why those distances between those servers are so important. So, Steve, if you want to explain that.
Yeah, it has a lot to do. I mean, we're all in the end serving IT customers. We're bringing all these services to them: power, data, cooling. And what they're doing is they're doing compute, right? And there's reasons why GPUs have gotten so power dense, right? They're nominally at 1,000 watts per chip, per GPU. And you got to ask, well, that seems like a lot of power. But the thing to remember is that they're incredibly efficient devices. It seems like a lot of power, but if you had to take a 1995 server and create the same compute as that single GPU, you'd be talking hundreds of servers. So they pack things in really dense because there's an economy of scale. Everything is close together. You can manage power flow really well, but more importantly, you can manage data flow because you can do direct access, direct memory access, right, over short distances. And then the other thing to remember is that these large learning models, when they're running these, they're built in clusters. So they're grouping together GPUs in these models, and those really high-speed data transfer only works over short distances. So they have, if you look at the different protocols like NVLink, right? It runs maybe 20 inches, so you can access memory and other GPUs over these short hops, and then you have to take another hop to go further. But there's a processing cost to take a hop. So there's a big drive to pack everything close together so they can run, in the end, what are a bunch of parallel processes together, right? And it's like a bunch of race cars. You're trying to launch them all at the exact same moment, and you want them to finish at exactly the same moment. And if you have to go out and say, reach out into a different rack, then you're going upwards in the rack to a switch, like an Ethernet switch, and then jumping to a different rack. And there's incredible costs in terms of time to do that. It's glacial compared to what the GPUs are doing when they're just jumping to each other within the rack. So that's kind of what drives it. That's what's making everything so dense. And I sometimes I look at real estate cost, right? So if you draw this line from the center of a GPU out to the parking lot in the data center, it goes from unbelievably expensive real estate to fairly reasonable real estate when you're in the middle of the car, and you just can't waste that space. That's why people are tight, tucking things in so tightly.
So no matter how much space I have, I just want to make sure I understand this. So no matter how much space I have, I can make a data center that's the size of a state. But the technology, right, the chip, is still going to constrain power density to be incredibly high, because they just, in order to meet those latency requirements they have, all the components of that cluster have to be within 20 inches or whatever you said. And so I always have to distribute thousands of watts to that tiny little space.
Yeah, they have what they call head and tail components in data transfer. So, I talked about those race cars on a track. If you ran 1,000 race cars in parallel on that track, right, you spent a lot of money to set up that process and launch it. If you have a race car that had to go to another rack, you have 999 race cars sitting there idle, waiting for that one car to get back and finish. So there's penalties involved. Yeah, if we spread things out and weren't efficient about tightly spacing, it costs that end customer, which is the IT customer that's paid to process data.
Makes me think of another point. So we often hear, experts, like really smart people in this industry. I mean, not often, but you do hear it, say things like vertical space doesn't matter. It's just floor space. But that, according to what you're saying, that just doesn't make any sense. I can't productively use an infinite amount of space above my rack, because that chip is like enforcing this like space constraint that I still have to have incredible amounts of equipment and power in a small location around that server rack, no matter however I design this data center. Do you guys agree with that?
Well, the vertical space, we've seen a higher need for that, so that you can serve the liquid cooling, with that chill water. You need space for that piping. So the vertical space has become very important as the density increases, because you need room for larger busway, multiple runs of busway, chill water pipes, and you want some separation between those items too, because you want to be able to, like, say, maybe put if you have the capability to do so physically in your data center, maybe put your piping under the floor and your electrical infrastructure and your data infrastructure high, so that if you have a leak in those pipes, then you're not causing damage to your equipment, either your distribution equipment or God forbid, the servers themselves, which are tremendously expensive. So you need height to make all that work in a small area to stack your infrastructure.
Yeah, I think there's going to be a lot of friction between, we're like the back of house guys, right? I always think of these hotels in New York City. Imagine the real estate cost in Manhattan, right? And a hotel wants to fill that with rooms, because they consider the end customer considers that the revenue producing component of their business. And there's always going to be a lot of friction. The back offices, when we're working in buildings, there's a whole different world where you walk through a little door and there's all these hallways and elevators for people that are working in the hotel, and all the facility equipment is back there. But I think what's happening is, there's already a migration to higher racks because of that GPU thing I was talking about, how you have short reach on high-speed communications. So the natural thing is to try to push the rack upward, just like you're in Manhattan. And there's going to be this friction between the service provider, back of house component of the business, where it's like you certainly don't want to be in a hotel and then the electrical and plumbing folks come in and say, hey, we need the top 20 floors for our stuff, right? There's going to be pressure between those two factions of the business.
Yeah, it makes me think of this concept in finance called option value. It's just the real financial value of having choices, having flexibility to make different decisions in the future. And another thing is, because we have so little, it's so difficult. For instance, we started talking about the article, right? And a year ago in the article, you guys were talking about predictions that, peak power densities would hit 20 kW. And now they've shot past that, and so we obviously have a really hard time predicting what power densities are going to be. And it takes 2 years to build these data centers, 2 or 3 years, I don't know. And so you almost like just the value of managing that space really well, like keeping as little equipment in that space as possible so that you have the option or more optionality to add taller racks if you need to, add more power distribution if you need to, add like chiller lines if you need to, is incredibly valuable. And I wonder, Mike, are you hearing like your customers like articulate that? Are they asking for more vertical space in these designs?
Yeah, and Mike, follow on to that question, like what is it? How far do you have to lead the target? Like when you're talking about a design right now, how long is it from where folks come up with the idea and when that data center is operating? Like how far do you have to look in the future?
So what we see happening is, our clients are having us designed around a pretty big end game, if you will, because when we see their actual ramp up to the load, it takes them years to get there. So, and where we see that is when we're shared the strategy with buying power from the utility, because they're buying power in kW blocks. So they have what they call ramp up. So we may be building, a 50 or 100 megawatt data center, but it may take that customer, if it's a single base customer, even a multi, in a colo, it may take them, 4 or 5 years to get to that load. So we're leading it off very large. And, when we were talking, Steve, about our rack densities of 200 kW per rack before, we were lamenting that, the server technology at the moment doesn't quite get there. So they're planning. So when this data center's done, they're anticipating the technology is going to get them so that a 200 kW rack's reality. And when you go to the symposiums and webinars and stuff, they're boasting much, much higher numbers, in the coming years, in short coming years, of even higher densities within racks. So they're leading us, but they end up catching up to it pretty good. Like the ones we've built already are at capacity. Of course, they're building more. So,
wow.
The stuff we started years ago and built and have gotten populated already caught up to themselves. So it didn't take very long. So you would anticipate that's going to continue to happen. So that is a challenge, though, to chase that. It's like, how far do you go with the density when you design it? Because, to James's point about the timeline, you can't just build this overnight. We're building them faster than anybody, believe me, and we're quite proud of that. But still, it's not an overnight. It's still even the fastest data center from the very inception, to the final build is a couple of years, even at the fastest pace. So you got to get ahead of it,
right? Lead times on equipment alone are a good chunk of that. Yeah,
exactly. Yeah, like we're seeing lead times for like, if you're not in line already, like say like you want a 2.5 megawatt generator and you want to get in line, you're waiting a couple of years just for that generator.
Wow.
Now if you're connected, you may be able to shorten that. But if you, I remember in a recent project we were contemplating changing the kW of a generator, but we had many of them, and the vendor told us, well, you're already in line for this one, so you have to get back to the beginning of the line. You won't get them till 2027. We're like, wow. So you have a lot out. Now that's an extreme case. Lead times have gotten a little bit better for a lot of equipment, but not much. We were thinking they were going to escalate in lead time, but there's a lot more players now because they see the opportunity. So you're not subject to just being at the mercy of the typical big manufacturers for, say, switchgear. There's a lot of people now making custom switchgear and sourcing circuit breakers elsewhere, and that competition is decreasing those lead times. They're still significant. Like for switchgear, you're looking, they'll tell you 40 weeks, but they're not including the submittal process, and they're giving you the lead time to ship. So you got to add some shipping time. You got to add a submittal time, which could be 1 to 2 months, depending on how well that goes. So you're looking at a year for switchgear, and pretty much most of the other equipment, at least. Transformers too can be quite a hefty lift too, especially because the data centers buy a lot of the same sizes they need, right? You're not buying a variety of, say, pad mounted oil filled transformers, a variety of sizes. You're looking at 2,500 kVA, 3,000, in those ranges. So you have a lot of people wanting the same product, and so transformers, they could be 80 weeks.
Wow. Yeah. Okay.
I think I totally underestimated speed to market, the value of speed to market. Because while you're talking, I was thinking about this stat I heard that these chips, these high performing GPUs, highest performing GPUs, become obsolete after 4 years. Like the technology and demand is changing so fast, like the customer demand is changing so fast that they feel like you have about 4 years to extract value from that purchase. But at the same time, we're talking about, so when you're planning to build one of these facilities, right, you have all that planning time, you have the lead times, you're making your best guess about what the densities will be, right? And you could get it wrong by the time you kind of actually turn the power on. And so it's such a risk. It seems like that the fact that this market, the chips are evolving so fast, creates this enormous risk and cost of just delays, just beyond loss of revenues. Literally, you could open a facility that some proportion of it is obsolete by the time it opens. Is that too extreme, or is that realistic?
It's realistic to a point, but the folks that are building the data centers, they're not building one data center and watching it intently as this is their one sole project. They're built. They have several in the works, all at different stages. So you take those lessons learned and you see the shortcomings of the one that's being built now, as far as how it's not keeping up, and then you adapt the next one. So they're building multiple data centers at various different stages. So they can adapt on the next one, but land isn't infinite. It's nice to say that we have all the land, and you have a lot of land to work with, and they are moving to more areas where they have accessibility to larger swaths of land. But you can still adapt and make these things larger as you move further out and away from urban, and ideally away from residential, right?
Yep. Yeah. Okay. This is such a fascinating topic. I could just pick your brain for another hour, but I'm going to, because we're also business, I'm going to shift over to the article. It's a good segue to talk about the article. And so, Steve, even though many of our millions of listeners might already know what fault managed power is, can you give a quick introduction to what the technology is, and a high level description of what the value proposition is for facilities like this?
Okay. All right. Okay. So fault managed power is a new class of electricity that is digital in format. So it sends electricity in what we call a packet. And it's a burst of electrical energy that goes from a device called a transmitter, which would be out in, as Mike talked about, out in the power block area. And then a receiver, which is inside the server rack. And that is what folks normally call a PDU or a rack PDU right now. And the other thing to talk about is that fault managed power, our brand name for it is digital electricity, but it's inherently safe. So you can touch, even at hundreds of volts, you can touch it with your hands, right, and not get hurt. It won't start a fire, but maybe even more importantly, in a digital environment, it's qualified to run in data channels. So it uses the same installation practices as Ethernet cable or communications cable, and it can run in the same pathways. So it's an installation instead of overhead busway, you're using data tray for digital electricity, and it's a structured cable or a communication cable that can even have fiber optics as part of that cable. So it kind of converges what we call digital convergence. It converges the pathways on one layer, and then it's a point-to-point architecture. Mike talked about how in the data block area you have N+1 or redundancy. That's it's not a 2N environment, which means there's not two of everything. There's just a little bit more than you need for redundancy on the outer edges. But with traditional AC distribution, when you enter the data hall, it's 2N. So you have two of the busways that Mike talked about. And within the racks, you'll have two rack PDUs to distribute power. So if you lose one, you're still running at full capacity. And fault managed power systems are what's called point-to-point architectures. So it's what a data person would be familiar with. Ethernet is a point-to-point architecture. You have a centralized hub that projects, individual channels out to the load. And so the data center architectures we're working on with fault managed power are point-to-point. So if you have, say, a fault or a short circuit or somebody touches the wires in one of the server cabinets, well, for one thing, they don't get hurt and nothing blows up. But the other thing is it only takes out that one individual channel, and there's many channels inside that server rack. So you don't need two of everything. It is kind of like the outer edge. The architectures that we run, they could be generally called an N+1 architecture. So, you might have 4 channels that go to the rack, 4 big channels, and but you only need 3.
So what equipment do you eliminate? That architecture you just described for fault managed power compared to the AC system, just list the main piece of equipment that you eliminate.
Well, yeah, the blocks that we talked about before, how to power flow through those is you have a transformer that serves a switchboard, and typically that's at 480 volts, and that's backed up by a generator that sits closely nearby. So that switchboard combines those two and acts as the transfer switch. It has the brain that switches between the two sources should one fail. And then that's distributing to a large UPS. And that UPS is designed to carry the critical load of that block, which is the servers. And in some cases, if you're doing liquid cooling, you want that to back up your liquid distribution in the form of the pumps and what's called the CDUs, because you don't want those you've got to have constant fluid flow. You can't even tolerate the 20 seconds it takes for a generator to come up. So after the UPS, that critical load will have distribution. This is where we talk about when Steve was talking about PDUs. So it'll go to another switchboard, distribute to PDUs, or power distribution. These are large floor-mounted, like vending machines or larger sized pieces of equipment that have transformers in them, and they will transform to a voltage of typically 415 volts because your single phase voltage is at that line-to-line voltage is 240 volts, and that's ideal for the servers. So that's why you see folks use that 415 volt as a standard. It's a large amount of data centers that we do use that voltage to distribute to the server racks. So those PDUs will then serve that overhead plug-in busway that ride above the server racks in a two one. And once you get to that point, as Steve mentioned, that is a 2N configuration because you want one bus from two different sources in case you lose that whole bus. And I think that's a very strong point for fault managed power because just to use some numbers, I'll use 300 kW. Say like your busway serves 300 kW in a row. And I know we're talking about larger densities, but let's use that number just to keep the math simple. Well, now you have to have distribution in that row for 600 kW. Okay. Because you want to plan for what if that bus fails? Then I need a whole nother bus above that row. Well, if you have a point by point architecture and you could feed that easily with 4 sources because all you're doing is routing these small cables in cable tray, you have the ability to serve that row with 4 sources. And with the fourth, that means that you need infrastructure for 400 kW in lieu of 600. So you can only imagine the savings, right? For every row, you're taking out a third of your redundancy need with doing that math. So adding that 4th bus, which is physically impossible in a traditional scheme because you can't put 4 busways above a single row of server racks. There's just not physical space to do it. You could put 2, and that leaves you stuck with 2N instead of 4 to make 3.
Wow, that's amazing. So just to reiterate, so you eliminate the generator and a generator switchboard, the UPS, the second switchboard for the PDU. I'm sorry, and then the PDUs.
Well, you wouldn't be that much. You would still need the major equipment. You would still need the transformer, generator, and switchboard. You would still need those pieces. Okay. Once you get to the UPS, now that's where things get different. All right. So ideally, how you would serve the fault managed power transmitters that Steve described is with rack mounted UPSs. So you have a row of racks that serves, and you could call it your fault managed power UPS, where you have a combination of rack mounted UPSs that go with their buddies, right? Their buddies are the transmitters. So Steve has adapted his product to match and scale them with how these rack mounted UPSs have grown and adapted over the years to get more powerful in smaller spaces. So you match those one for one, and now you have a fault managed power UPS, which has a transmitter and the UPSs and the batteries in a similar rack lineup as an AC UPS and battery rack. So in that case, you're not sacrificing space, the space you've allocated for your AC UPS. You have not sacrificed that space now. And then what comes out of the transmitter are the cables, and the class 4 or fault managed power cables come out of those transmitters, and that's where the difference is. Those cables ride on cable trays directly to the PD. I'll call them they're the rack mounted PDUs, not the floor mounted, but they're basically the receiver in which the server plugs into, and that's direct fault managed power DC to straight DC. And that's what those receivers are doing, is transforming that monitored DC into straight DC. So therefore, you eliminate the downstream switchboard of the UPS. You're replacing the UPS with this more sophisticated UPS, and you're replacing everything downstream of that. So you don't have that critical distribution panel. You don't have the static switches. You don't have the PDUs. You don't have the busway. So and if you think of all those pieces have connections that need to be maintained because they're all failure points. So you think of all the failure points and all those connections and all those IR windows that you need to keep an eye on to see if they're overheating. It's a lot of elimination of failure points, and also it simplifies greatly your maintenance. A lot of big costs for data centers is maintaining all the sophisticated and expensive equipment because outages are very, very bad for them, obviously. So, there's a lot of maintenance to ensure that they continue to run properly, looking at those IR windows, make sure those connections aren't getting hot. The fault managed power eliminates all of that, because once you leave the transmitter, all you're doing is the other end is the receiver, and then that's your power source for your server.
And how much vertical space? Like, it sounds like you can put, correct me if I'm wrong, so I can put the digital electricity or their class 4 or fault managed power cable in the same cable tray as the data cable, but would you do that in practice? Could you do that in practice?
You could. I think when these densities increase, you probably wouldn't, but they'd be closely nearby. Mm-hmm. And because you want a little bit of space, you want you have a limit to a practical limit, I should say, to your cable trays, because you don't want them to ever grow over 4 feet, because then you need sprinklers underneath them, right? In the sprinkler code. So you want to keep them, typically at 3 feet, because when it gets to cable tray, you need to be able to reach over and get in there too, to add cables, replace cables, whatnot. So there's a practical width there that you want to live in. And at the densities we're talking about, how we're growing, you're going to need a lot of cables, but you could still provide that amount of power with cable tray in lieu of busway. The situation that I described before with multiple runs of busway, that takes up a tremendous amount of space, especially when you have to introduce a third bus or extra distribution to pick up more servers that fall beyond the standard means of what's available in those products. So having the cable tray just get a little bit larger to add more fault managed power cables is a lot easier than adding AC large ampacity distribution equipment.
Did you guys come up with an estimate on how much vertical space? It sounds like you obviously clearly removed tons of equipment, and I'd be curious about like the percentage, like what's the percentage reduction in equipment. I also want to know the percentage reduction in cost. But before I get there, like, did you estimate how much vertical space you save with this architecture, the digital electricity architecture?
Yeah, I don't think it's too early. I mean, the paper will be out soon. I think we're pretty confident that it's coming out to about an 80% reduction in cross-sectional area. Because the thing that we're talking about is that, a lot of folks think that it's all about reducing copper cross-section. And, there's talk now about going up in voltage, right? And that helps you reduce the amount of copper that you need to distribute the power. You need lower amps, so you need less copper cross-section. But the thing that makes electricity big, electrical distribution conventionally, is the safety aspect, because Mike opened up with that about how safety is a big concern. And I'm not going to say that data centers aren't safe. They are. It's kind of like, what do you have to do to get to that level of safety? And with conventional AC, you have a lot of stuff that you put around that copper. It's kind of like a wild animal in a cage, right? And you have to keep it in its cage from hurting people or starting things on fire or arcing off. That takes a lot of space. And so the 80% reduction, it has something to do with the voltage. I mean, but we actually operate at similar voltages to the 415 three-phase power that Mike's talking about. It's just that we don't need all that extra stuff. We don't have the disconnects and the switches and all the sheet metal that goes around busway and the keep-out areas. That's where all the savings are.
That's amazing, though. 80% is amazing.
Yeah, and the safety is a massive advantage, because if you think about the components that we discussed that we're replacing with the fault managed power, where does that fault managed power run? Well, that's in the data hall, because all the equipment upstream of that is located outside of the data hall. So wouldn't it be great to tell a client that's in your data hall is, this data hall, your racks are safe from any electrical injury. It's safe from fire. You don't need arc flash stickers, because, to Steve's point, you could touch this stuff. It doesn't tickle, but it doesn't injure you. It doesn't burn you and certainly won't kill you. So you can't say the same for any of the AC components I described. They're very, very dangerous. That's why they're in big metal enclosures. You have many safety precautions and stickers on them, as to what the ramifications are. If you open one or work off one live, you have those arc flash stickers, and you require your PPE to even think about doing that stuff. But now with fault managed power, number one, all you have is cable. All right, there's really nothing to maintain. But even if something rubbed off, like an insulation rubbed off, that channel just goes down and instantly, within milliseconds. So there's really no risk of fire or shock, and when it goes down, because one of the other benefits I learned about fault managed power is because you're monitoring those channels constantly. At 500 hertz, you're monitoring those channels to make sure that the receiver's getting every bit from that transmitter. You now have the most granular power management system you could ever want. Every channel, the watts, every statistic about that in real time. So it's recordable. So you now have a very sophisticated and granular electrical power monitoring system.
How about speed to market? Like that's what we were talking about. Like how much faster does it actually? Do you anticipate that actually increases the speed that you build these facilities?
Yeah, I think from a labor standpoint, I think the lead times for the equipment, and Steve, if you correct me if I'm wrong, but they're significantly better than some of the year long, the 40, 50, 60 weeks we were talking about before, or higher. I believe that the speed to market just for the pieces are shorter, but the labor, because this can be installed because it's a class 4, an NEC class 4 recognized installation. You can use an IT technician to install these components. Now, it's a skill set, no doubt. It's not, it's still very skilled labor, so it'll tend to be a cheaper form of labor, if you will. But that's a different level of cost because you're routing cables in a cable tray. So the labor is going to be much less on a per hour basis, and also the techniques involved are, instead of pulling wire and conduit and making torqued connections with 600 volt cable, that's a very, very skill set. So and time consuming, whereas laying a cable in a cable tray, is not. It's a much more simple process.
Yeah, and what we see in our other projects is that often people will still use electricians because they're in there anyways, and they have excellent wire management. But the amount of labor it takes to distribute the power is so much less that it just doesn't. The financial impact is negligible.
I think we ran the first study all on union labor, and
we did.
Yeah, and it's fine. Many of our installations are done with licensed electricians, but it's just less hours. So you can use a common crew, and there's also your utilization of apprentice labor can be better distributed for like cable pulls and things like that.
So what was the cost impact? Like, are you willing to talk about the new paper's estimates today, or do you want to wait?
Oh, we can't. We're not done.
Oh, okay. Okay, that's too bad. Well, people have to keep checking in our websites to get the update.
Well, that's the big finish, right?
Yeah.
I guess we'll see. I mean, we exceeded 30 in the first analysis. It exceeded 30% overall installed. And then I guess what we'll find out this time is how it relates, because that was at 25 kilowatts per rack, and this one will be at 200. So I guess it'll be how it relates. The paper is a little strange because, as Mike pointed out, the rack density is leading the available sort of. If you look at, say, a Dell or a super micro GPU server right now, they can't fit into a 200 kilowatt. The density isn't there yet. So we got to sort of, fudge around some of that stuff. But I guess we're going to find out how it scales to really high power densities versus 25 kilowatts, which actually is high power density. It's the new high.
Right. And a lot of it was attributed to, in the first go around, the significant savings was in the labor.
Yeah.
All right. So,
yep.
Oh, sorry, Steve, I cut you off. Go ahead.
Oh, I was just going to point out, I think we got to work out, Mike, like the overhead, the busway distribution in the AC case, we don't really have a good solution yet for getting it to the racks. I mean, I guess you can go 20 feet high or whatever, but yeah, it's a little messy right now. That we still have some work to do there.
Well, at that, because you have a road that's 2 meg, right? So you do have to have a tertiary level of distribution. You can't just get it from both ends anymore. So that's the tricky part of having a busway run over the other busway and then jog down and pick up those last 2 racks, unless you want, to serve those stray racks, if you will, with just straight outlets. But that becomes a non-ideal form of distribution for those racks, because you have 2 different styles now, which is not right.
Let's wrap up with a prediction. So, we're saying that using fault managed power, you're eliminating 80% of the equipment that you would typically use for distribution inside a data hall.
Whoa.
Oh, was that it?
Where'd you get that? I like that jump. We said we had an 80% cross-section reduction in
okay, good.
I don't know about 80. Good. I don't know. I don't know about
space reduction.
Yeah. Equipment. Well, depending on how you define equipment, right? We took out all that stuff that Mike's talking about. I don't know if we want to count it as weight or volume or whatever. There's certainly a lot of weight and volume that's taken out of the white space or the data hall.
Right. Yeah. I mean, and that's at the densities we're talking about, that becomes significant, because those PDUs, they'll sit along the perimeter. You have to find room for them. Like, you could get slick and start putting mezzanines and stuff, but that becomes tricky for maintenance. But they take up significant space at these densities, and that would be much more useful as more rows of servers, right? So, that space that you're taking out, with those PDUs, that's significant. And also, your static switches and whatnot that you're able to remove, those take up space too, because they need to be in conditioned spaces. Those are sophisticated pieces of equipment that require a decent level of conditioning. They just can't sit outside or sit in an unconditioned space. They have temperature limitations, like most equipment that have processors in them.
Okay, so we're getting rid of, in terms of volume,
tons of stuff.
Tons of stuff, right? It's way easier to install. It's safer. It's smarter. And at least for the 25 kW data center, a rack, it was less expensive. So my question is, first, do you believe that, in some amount of time, fault managed power is going to be the standard for power distribution in data centers? And if so, how long until it's the standard?
Well, from my side, I think what I see is it's gonna take a leap from an owner to do that, right? Especially at a large scale. I think how it will happen is through some pilot sites to show that it could work, and then scale from there and show how it's scalable. I think it will be, and then once that occurs and shown as proven, then you'll get more owners ready to take that leap, because it would be you're asking them to change, their topology, take a big risk, and they're building these things so fast. Would they risk, and from in a colo environment, that would be the biggest challenge, because as far as like a single user data center, they might be more willing to take that risk because they know their servers would adapt well to getting that direct DC from the receivers, which you can't assume is the case for a colo, because a colo owner isn't going to know specifically what equipment's going into those racks. So you have to know first off if it's going to take that DC. So it's going to be a tricky environment in the colo environment, but a single user data center, I think those would probably be the ones that take the first leap.
Yeah, that makes sense. And yeah,
Nothing
James,
to add to that, Steve?
we have some tiny pilots going on right now. So it's getting some mileage on it, but as Mike said, yeah, we don't have anything at scale yet. It will take it, we're going to keep talking and promoting, and use our relationships, and eventually we'll get there.
Yeah, because today that technology exists, it's in the code. So eventually, it's a better form of power distribution? There's some pathway that it has to go through in order to be adopted in the data center space. But it's really hard for me to believe that it won't be.
Yeah, I think we started in our other markets. We always started by, the advantages, the mix of the value proposition with how much in total installed cost, and the other values it brings. Like we talked about data analytics that are inherent to the system, and we know that we have to really be impactful. The 30+% installed cost CapEx has always been a formula that we've used in Volt Server to get people to consider it, right? To consider taking some risk and then throwing everything else in. And that's how we get first adopters. That's how we've traditionally got it. As you know, this is a new market for us. We just started on this one, but we use a similar formula in our other market spaces. So maybe somebody listening to this podcast.
Yeah, we'll take the chance. Yeah. But it's great we have partners like Mike that's helping us champion this and promote it and find, understand the new possibilities it creates. Mike, you're so smart and you just know so much stuff. I would just love it if you were always on this podcast with us.
Yeah, happy to be here. I appreciate you having that, having me join you today. It's been a lot of fun. But the nice thing about the fault managed power, just to build on that, is if you have an existing data center that still has halls to go, portions to go, this technology could still be adapted there because it's all downstream of the UPS. All right. Mm-hmm. So a lot of cases that when you have shell space, you don't have your UPSs, you don't have your transformers, you don't have your generators yet. And all that's the same. It takes up the same room in a fault managed power solution because you still have those components. But it's just once you get to the UPS, that's where you adapt it. And then it's all downstream from there. So if you have one hall that has, say, 5, 6, 7 power blocks, then you just build out those blocks to have fault managed power distribution. You have a single tenant that has the equipment that accepts that DC power, which isn't a stretch at all. That data hall could be fault managed power, even though if you have AC and all the other ones. So don't have to commit to it for a whole building. You can commit to it for a portion. So that's a nice little feature to it, so that maybe there's more willingness to take a little plunge in a smaller area once the owner's comfortable with the technology.
Yeah, I agree with that. And I think that's what we've seen, how we've penetrated other markets, is often it's a hard retrofit. Like you're trying to get more power into this tight location, which is power constrained for some reason, like a data center that was built for, 8 kW racks, and suddenly they need to install a 30 kW rack, and they just can't squeeze. They can't get the power in there. If they try to do that work, they risk, causing a disruption to service. And it's much easier to basically snake, a skinny little digital electricity cable through whatever pathways have available and deliver that power to a location. And so I agree with you. I think an application like that will likely be the way we penetrate this market.
Agreed. It doesn't have to be all in.
Yeah. Anyway, so I think that's a good place to wrap up. Mike, thanks for joining us. I really enjoyed speaking with you. I hope that you could join us on many more of these podcasts.
Well, thank you. Yeah, I really enjoyed the time here. I appreciate you guys having me on today. It was a pleasure to talk about it, and I'm excited for the future that fault managed power could bring to the industry.
And if the audience wants to download the paper that Steve and Mike published last year, a comparison of fault managed power and traditional AC distribution high performance data centers for, I think it was a 20 data center built around 20 kW server racks or 25 kW server racks. Yeah. It's on, I think it's on both our websites. And I guess when can we expect your new paper around the 200 kW rack design?
Is that 3 days, Mike?
Coming to the theater this summer.
All right, fair enough. Summer's a good target.
All right, so we'll post it on social media when it's done sometime this summer. All right, thanks everyone, and see you guys next time.
All right, thanks, James.
Thank you.